Welcome again to another MTH218 class. So this week is two things. One, which is probably multiple minds, is the assignment's due tomorrow. First assignment's due tomorrow. So I guess the first question is, do people have any burning questions that we need to cover first? And certainly someone asked me a question beforehand, which I'm about to go through. You can see at the bottom of the slide there. So if you've got any others, please throw away. Once we've gone through those burning questions, the next thing I'm going to do is to move on to the next segment of the subject. I'm looking at multiple integrals. Okay, so let's look over. So the question that someone asked me was about how do you go about sketching stuff in 3D? That seems to be the big question. So I just want to try to go through this sort of question a little bit. It's not identical to any of your assignment questions, but some of the broadly speaking things are similar to it. So this is a quadric surface. I've already completed the square for it as written. And so if there's a question in assignment, it might be similar. So I already completed the square. I want to try to work out what it is. So if I take traces in different directions, so if I fix, for example, the z's, and if I fix the x's, then you end up getting in both cases hyperbolas. So I'm skipping some of the steps here, but if you fix z and x's, you're going to get hyperbolas cropping up. And since you're getting hyperbolas in two different directions, that immediately tells you it's a hyperboloid. And so, in terms of a picture, when you fix values in two different directions, you get the same sort of shape. So hyperbolas in this case, they would be what I would think of in my picture as the horizontal cross sections. So that's cutting it. So the z, I'll say that again, the z and the x then are going to be my horizontal axes. So they're going to be the ones in the plane. So when I draw my picture later on, x and z will be in the horizontal, and my other direction, so z in this case, is going to be my vertical. And so these two directions give you the horizontal axis directions at least. So fixing them basically go up and down, but anyway. So two different directions give you the horizontal ones. If I then fix the third direction, in this case y, that tells me what type of hyperboloid I have, or what type of anything. So if you had two directions which are parabolas, if you paraboloid, the third direction gives you the type. So if we fix y, in this case we're getting x minus 1 squared plus z minus 2 squared on 4, or 2 squared, is equal to 1 plus y plus 1 squared. So because we've got a sums of squares, these are ellipses, and because the right hand side here would always be greater than 0, it's always at least 1 for that matter, there'd be no break. And so since we have ellipses with no break, then we know this is a hyperboloid of one sheet. And this different direction, these ellipses, will end up being the axis which corresponds to, is easiest to draw vertically. Now, how do you draw it? So now we know what type of shape it is. It's a hyperboloid of one sheet. How do you go about drawing it? Well, what I would do is I would pull out a picture of what a hyperboloid of one sheet looks like approximately, and go from there. You could be a little fancier to begin with, which I'll try to be. So the way we draw them really is these traces here, these ones that really determine what the special type is, are the key ones to draw, and they're going to be y's are different vertical values, and cross sections with fixed vertical values end up being parallel to the bottom plane. So these would be all ellipses. And if you look at each ellipse, the major axis would be twice on the z direction as an x direction. So I'm thinking in my mind that I'm drawing it all parallel to x and z in the horizontal axis and my y is my vertical. And that's what I have in my mind, just over on one side of the moment. I'm just going to draw my picture over here though. So I'm going to draw it without axes to begin with. I actually find that easier. So a hyperboloid of one sheet pretty much is look something like that. Does it look like normally? So I can just draw that picture. But since I'm going to try to draw it really, well, a little bit more accurately than that at least, they're going to be ellipses and they're going to be a bit longer in the z direction. So at the central ellipse will look like this, bigger in the z direction, and then as they go further up or away from the center, they'll be bigger ellipses. And then just draw some lines. So that's my rough picture of my hyperboloid of one sheet. So just drawing 3 traces for different fixed y bays. The center is bang in the middle of it here, and that's my rough idea. So that's a hyperboloid of one sheet. We need a few things to make it understandable what it is. So I think the first thing is you need to sort of pin it down into space. And the easiest way to do that is to label just some key points. In this case, the center would be fine. So the center, which is my little dot here, is pretty much when all these complete of the square terms are equal to 0. So when x equals 1, y equals -1, z equals 2, just reading off. So 1, -1, 2 would be where all the different completed squares are equal to 0, and therefore that will give me my center. That sort of pins it into space. So that's the first thing. Next thing is it can spin around widely, so you need to orientate it. So you need to label enough to give the idea of which direction it's pointing in. And you can do that using the principal axis, like I got over here, just put on the diagram. At least you know that it's pointing up and down in the z-y direction. That'd be something. I hope it's still there. The other way of doing it is to put axes back, basically align them exactly to this shape we've got here. Can you still hear me? I've got lots of thunderstorm here and it's worried that my thing's going. Okay, thank you. So what I've done is I've just drawn axes through my shape after the really lying to my shape, not to the principal axes. Now these aren't the same ones, so I'm going to label them properly. So this top one up here is parallel to the y's. So pretty much it's when the other values are fixed. So it's when x is fixed, and it's going to be fixed through the center, so x equals 1. And when the z value is fixed, which would be 2. So pretty much that's my axis parallel to the y one. And then I can find axes in the other directions too. So this axis would be the one parallel to z, so it's from the other variables, x equals 1, y equals -1. And lastly, this would be when everything but the x is fixed, so y equals -1, z equals 2. So I've got axes through the center. So basically the labeling center fixes in space, and these axes just determine the orientation. And that's enough to give you a qualitative understanding what the surface is. So you can see quickly, hopefully if I draw okay, it's a hyperboloid of one sheet, then labeling the center and the axes then fixed in space nicely for you. So that's what I'm sort of looking for in assignment, in a similar question, is draw the shape, and it's probably just easier to free draw it and then add on the axes at the end to fix in space. That is not the only way of doing it though. Now, some of you don't trust your own drawing and prefer to use Maple, which is fine. So let's just show you how to do this in Maple. So first you have to do with plots. If it's not big enough, just let me know. It might not be enough. Let's so I want to plot in 3D. As a matter of fact, I want to do implicit plot in 3D the function I've got. So it's x minus 1 squared plus whatever it is minus z plus 1 squared plus z minus 2 squared on 4 equals 1, I think it was. And just give some ranges. So I'm just going to give plus or minus 5 about the central point. So 1 minus 5 to 1 plus 5. Z equals minus 1, minus 5, minus 1, plus 5. And for the Z direction, which we've already worked out from a picture, it goes twice as much in that way. I'm going to do 2 plus or minus 2 times by 5. Let's see if I haven't typed, hopefully I didn't know what I'm saying. So if I do all that, basically this first thing is the function I've got, and all the others just some ranges of x and y's. And I said, I've not even thought, I've just plus or minus 5 from the center. And you can spin it around to make it look better, whatever you feel like, etc. And you see if I spin it around, that's roughly the picture I drew before. So the question is, well, that doesn't label many things for us. So can we put a few more stuff in to make it a bit easier to see? So you can do a few other things. So I'm just pressing a command. I'm putting Shift Enter to put it all on, to have it on multiple lines. So you can go axes is box, just to put some labels on the outside of it. To make it easy to put labels on afterwards, you can do the transparency, if I can remember how to spell it properly, equals a 0.7, make it more see-through, so I can put some labels in a second. You can bump up the accuracy by num points equals, say, 10,000. So we try those. You can see we've got lots more detail, more transparency. If you want the what's the word for it? Shading? No. If you right-click, you get all these different things to remind me. So style, that's what I'm looking for. So style equals surface, and you can just see the surface itself with all the lines on it, and it's got a bit of transparency. So in order to add some labels, again, if you feel like it, I want to give it a name. Let's call it P1. Then I want to add a text plot. So T1 for text plot, say. So I want to do a text plot in 3D. And this allows me to draw some stuff. So I open square brackets from a list of stuff. The first item is in square brackets. I want to label the center. So the center we worked out is 1, minus 1, and 2. And then on top my text is, that's something like, say, center, whatever it was, 1, minus 1, 2. Close my section off, close my brackets, close my little thing off, and then I want to display all of these on the same graph, so P1 and T1 together. And that's put it both together, and you can see the transparency, you can see the text through it, and you can see it's labeled the center in the middle of it. And if you wanted to do other things, like you can have a line, for example, let's draw a line. So I want to do a point plot in 3D, and I want to draw a line, just that central axis like I did in my freehand drawing. So the line would be from 1, minus 1 plus 5, sorry, minus 1 plus 5 to 2. That would be the up above here somewhere, if you can see that. And then I want to draw the other end as 1, minus 1, minus 5 to 2. Close my list off, and then I want to say I want to have connect the dots together, so it draws my line for me. Better make the color black so I can see it better. Semicolon and then go enter. See what happens. And it didn't like me. What didn't it like? Oh, let's make it a 3D rather than 2D, and it might like it better. Extra square bracket to open it up. Yeah, there you go. So for now, I can spin it around to make it look a bit easier. You can see I've got my hyperloid and I've got my central axis in the middle of it. Other things that are useful, I'm looking at it. We know it's different shape in the X and Y direction. So if you put a bracket, scaling equals constrained, it actually captures that captures the fact that there's a different width there for you. And I could add an extra label. So I could just go, well, say it 1, 4, 2. I could put another one saying central axis X equals 1, Z equals 2 on there. Bit of an extra back to make it work. And then that's my picture. Let's make it bigger. A chance of seeing it. Spin it round to make it a bit easier to see. Maybe. So that's my picture that I've used Maple to help me out a lot with. So I've made it a little bit transparent to make it easier to see, and then just label axis stuff on. So what do you need to do for your assignment? All this text here, which I've just did. So let me just copy and paste it into the chat box, which might make it easier to see or get later, etc. I'll also put up the notes that I'll upload later. The other thing with these sort of stuff is, what I really want is, one, you got to draw the picture. Computer's fine, as you can see. Then label enough so you know how it pins in space and some sort of orientation. And so normally, to pin in space, just label a key point or two. So center, vertices, that does it quite nicely. And then you need to try to give it the orientation. And orientation, as you said, I can label axes through it. And as someone's asked, you could specify it using vector notation quite fine. That's exactly right. You also could do it by having the boxed axes around the side here. And if you look at the assignment, it's only worth 1 mark, so it isn't totally worth 20 marks. So as long as you're given some indication that, yes, I know exactly what you refer, I know where it's basically pointing, that's fine. You realize that trying to free draw one and using the principal axis to give the orientation ends up being really hard, just because you've got it's really hard to work out the depth of where the picture is, which is why I like putting the principal axis on myself, but you can do it otherwise. So hopefully that gives you some, yes, you can use other sort of things to help you out. So that gives you some sort of tips for what I'm looking for when drawing pictures, and perhaps some ways of doing it, either using Maple or by hand. In your exam, you're going to have to draw some 3D surfaces, not terribly many, but a few, and you're going to have to free draw them in that case. And that's sort of the quality I'm looking for. Maybe you can draw a little bit neater than me, but that sort of level is what I'm looking for. So I hope that gives some sort of help for that last minute help for people that need to. Before I move on though, do anyone else have questions that they're sort of burning to ask about assignment 1? They're just last minute help as they're doing it tonight or tomorrow night, as the case may be. If not, I'll move on. Find it. Okay. So once we finished assignment 1, and some of you guys might have already done so, the next thing I want to do is to move on to the second part of the subject, so chapter 2 effectively. And this is looking at how to extend integration to functions of many variables. So we know how to integrate one variable. How do we integrate a function with multiple variables? and that's what we want to focus on. So basically stepping up, integrating over one variable just really means integrating over just a segment of a line. That's pretty much what it corresponds to. And so we want to integrate over different sorts of things. So we want to focus off bits of 2D or 3D, etc. It's ultimately what we're heading towards. And so the technique is called multiple integrals, is the basic idea. So how you integrate depends upon what sort of region you're integrating over. So when you got, for 1D, it's the bit of segment line, that's the beginning and the end of the story, you have a bit more different types of regions you can integrate over. And so how we're going to do is we're going to split up this discussion by looking at different types of regions you integrate over, just to have of increasing difficulty and looking at how to integrate over. So what we're going to focus today is integrating over rectangles, essentially. Then we'll move over to more general regions called type 1 and type 2 regions, and look at circles later on. We need, as we go through this, we need to look at some techniques for how do you actually do it. So as I said, I'm most interested in analytical methods, so not approximation, so going direct to someone put it before. So I want to look at analytical methods. The main way of doing them is the iterative process, which we'll see in a second. But there are other techniques we need to start developing. And so we're going towards them. So the main techniques is either doing them directly via an iterative method. Changing the order of variables is another method we need to consider later on, which I was planning to touch on today, briefly at least. And then we need to, and the other one is transforming variables, which is a beefed up version of integration by substitution, effectively. And so we need to look at that one, and certainly look at that in the context of, say, polar coordinates. So that's what we're heading towards at the big picture. And so by the end of chapter 2, we'll be able to be looking at lots of different types of integrating over 2 variables or 3 variables, and be able to have a few different techniques that we can try to use to solve them analytically and be able to produce an answer. And we'll see some applications, what do you actually do with them, like why would you ever need to consider them, etc. So that's sort of an overview of what we're going to look at. So taking a step back, first of all of these double integrals really require knowing the idea of partial integration. And snapshot, thank you. My things aren't working. So partial integration pretty much is the opposite of partial differentiation. There is no special notation for it. You just have to let the context decide, really. So you just draw it with the normal integral symbol. So we know that the partial derivative of z with respect to x is given by this expression here. Then z would be the partial integral of this expression. And I write down dx, not partial x, just dx. That's sort of notation I use for it. And then basically integrate. And the main rule with partial differentiation or integration is you're keeping everything else constant. So we're only integrating the x's directly. Anything like y's, we just assume they're constant. So the integral of 8 would be 8x. The integral of x squared would be x cubed on 3. The integral of a constant, like 4 minus y squared, would be just that constant times by x. So a straight partial integration would be just these terms. You can have a constant, so plus a constant. And when I say plus a constant, that means it's a constant with respect to x. But it could be a variable or anything else. So since we have x's and y's floating around, it's constant with respect to x, but it might be a variable with respect to y, for example. So that's how you would do a straight partial integral directly. Most of the applications that we're mostly thinking of for quite some time really will have limits for these things. We'll have limits on these. And when you have limits, this constant of integration doesn't matter. You can just always omit it. But we will look at situations a bit later on, more in the third part of the subject, where we do need to worry about this, so which is why I mention it now. So partial integration, partial differentiation is a simple extension. Partial integration, again, is not a same sort of idea, essentially. So that's the first sort of thing we need to do. What we're more focused on is, as I said, the definite versions of these, not an indefinite partial integral. Okay. So what we're focused on is the idea of double integrals. So let's just scribble around a bit. So a one variable integral is really the integral of fx dx. What that corresponds to is you've got some sort of curve out there. So y equals fx. And what the notation really suggests is you end up splitting up your region into thin rectangles. The height of the rectangle is given by the value of the function at whatever x value is. The width of each rectangle is a small amount of x, so make them really small. And then this little rectangle we've got here, this is a bit of area. So it's got area to it, so rectangle's got area to it, but it's a really small area because you make it really thin. This small bit of area would be its height times by its width. And then what we want to do is, to work out the total area, we just sum them all up. And then we write down a big S for sum, which is the integral symbol. And so when you're summing up lots of small bits of area, you get the total area. So this one variable really is, I'm summing up lots of fx times by a smaller bit of x. That's where the notation comes from. And indeed, that's how you can work them out approximately using numerical techniques for that matter too. So what I want to do is I want to try to extend that idea to not just summing up over one variable when you've got multiple variables. So here's the picture. So take a step back. This sort of, the key application we had for one variable integration was always area under the curve. That's the main idea. So when we got double integrals, is integrating, we've got two variables present. Really, it's the idea of working out the volume under a surface. That's pretty much the problem we have in mind. So the second picture is probably a bit easier. So we've got a surface here in blue, sitting above a rectangle is what we've got focused for the moment. And so what we're doing is we end up splitting up to work out the volume, at least theoretically, we split up into lots of different segments, so different rectangular prisms. The height of this would be given by the surface, so fxy, for example, so two variables. And then the width of this, let's just, I'm going to scribble all over it, so I need to copy it. So the width here would be a bit of x, a bit of y, and a bit of x. And so this volume, this small bit of volume, would be the height, fxy say, times by a bit of x times a bit of y. And these x's and y's are really small. And then to work out the total volume then, we need to sum up all these sort of things. But we need to sum in both directions. We need to sum both x's, so we need to sum all the x values, and we need to sum the y values. So we write down two s's, or two integral symbols effectively, to say we're summing in both directions. So the notation, and all we've got is notation so far, is the volume under a curve would be the double integral of a function dx dy. And equivalently, you could write dy dx as well. How we write it down, like we want to write down limits, the inside sum corresponds to the intervariable. So let's write it in colour. This sum symbol corresponds to the x. And so in this my picture here, x goes from A to B. So write down my limits for the x's along next to that one, and for the y, that's the outside one. Outside, the y would be from C to D over here. So this notation suggests inside matches up, outside matches up. And so these just indicate what the limits in the different x's and y's are. And so basically what we're doing is we're summing x's from x equals a up to x equals b. That's what the notation is actually trying to suggest. How we do it isn't always that way, but that's where the notation comes from. So let's just do one example for the moment, and then we'll talk about how to do it in more general terms. So what we're trying to do is we're trying to integrate twice, so it's called a double integral over a region R of a function 5 dA. Now, you can see a few things that when we want to write this stuff down, I said before, we have the value of the function, and I normally write things as dx, dy, but I can also have written it out as dy dx. So I can write it out, instead of a small bit of x and y times by y, I can always just call for short that is a small bit of area. So for abbreviation terms, I can write this as dA. I don't do that very often, actually. It's only when, so most of the time, the order makes a big difference of how you write the rest of it out, and therefore it's usually good to write dx, dy, or dy dx, whatever the case may be. But occasionally dA is just a nice simple way of writing it down. And certainly that's just a convenient placeholder. Also, instead of writing all limits down, sometimes just put one letter to describe the whole region. And I would often ask questions like this way to force you to have to work out the limits yourself, which is one of the skills that we need to develop. So let's just have a look. A good way of tackling any of these sort of problems, by the way, is to draw the area of integration. So draw the, so if you look at the picture previously, this surface is hard to draw, like we've just spent some time with today already, but we can draw in 2D much easier. And so labeling, so drawing what the 2D region the whole thing sits above is much easier to work with. So in this case here, it's actually okay. I can work out what R is, the region of integration. So I've got my X and Y axis here. Then this region is everywhere between X equals 1 and 3, and Y is everywhere between 2 and 4. So it's a rectangle. Like that. So that's my region of integration. And that's normally doable to work out. This one's very straightforward, being a rectangle, but others will get harder later. So that's a really important thing to do, I think, just to draw that, just to give a sense of it. And certainly, when you see it visually, that often tells you how to do it later. Yes, it's a square, unlike my drawing, thank you. But yeah, so squares and rectangles you treat the same way, unfortunately, so I can get away with my poor drawing here. But yeah, so if it was a circle, for example, that would dictate strongly how you solve the rest of the integral. Being a rectangle tells you it's a simple one, fortunately. We're going to try drawing the whole thing in 3D too. So drawing in 3D, this is my X, Y. So this is my square. And the plane, so that's my region I'm integrating above it. And so I have a function, and the function I've got is 5 everywhere. So, which I actually can draw. So the actual surface that I'm actually trying to integrate and work out the volume under is this one here, which is at a height of 5. So the Z value is 5. Put some dots here. So that's my surface. And as you can see, well, when I try and work out the volume underneath this surface, it's just going to be a rectangular prism in this case. So this corresponds to a volume, and it's the volume of the underneath the surface, so volume of the rectangular prism. So without doing any calculations at all, like not really doing any integrals as such, because it's a rectangular prism, I can work out the volume of this rectangular prism. So, remember how to work out areas of, volumes of rectangular prisms? So to work out the volume of a rectangular prism, which you can please type in the answer, which you reckon the answer is, you need to know the length of all the sides. So the length of the sides here are 2 and 2, which are probably easier done in the 2D version. You know the height's 5, so the volume is going to be length times by breadth times by height, which someone has correctly said, thank you, is 20. And so we can evaluate this integral without necessarily any calculations. It's just about understanding what it's trying to ask. So this really was just about realizing a double integral really just corresponds to a volume. And so sometimes realizing you've got a really simple shape up your hands is actually the easiest way of doing it, rather than trying to do any other calculations at all. So, question is, does the orientation matter? The way you're supposed to draw axes, like I've got here, is you're supposed to use the right-hand rule, and that is if you go from, which I've drawn incorrectly actually, which is what you are asking. So normally you go from, if you move your fingers from the X through the Y-axis, the Z-axis should be in the direction of your thumb. So if I'm doing it from here, if I'm doing, so X, Y is curling around this way, the thumb will be pointing this direction. So I actually got the Z-axis run the wrong way. So thank you for pointing out my error. Does it change the answer? Well, things like volume don't get changed by an orientation change. So it doesn't matter in that sense. It would make a difference for things that do depend upon orientation, which we do look at later, unfortunately. But visually, this is just mostly a clue rather than anything else. So the question is, well, this is all well and good for volumes of prisms. What do you do when you don't have a prism? Well, let's just go back to our little picture. So what we had a rectangular region. We had our sort of surface sitting above it up there. We were one way split up into rectangles. What we could do is we could think of a whole rectangle underneath, some sort of strip. This was the X, that was the Y direction, doing it properly. So this would be make it really thin, so it would be a really thin strip in the Y direction. So I just drawing straight lines is hard. That's sort of my strip. So what I can do is I can break my volume up into all these different sort of strips. So, and this bit of strip here is a bit of volume. So this volume, and how you work at the volume is it's close to it's some sort of prism really, and the prism, an area of a prism would be the cross-sectional area times by its width times by dy. That's sort of what this volume would be. So the total volume will be summing up all these different ideas. And so using normal single variable calculus, this would be the single integral of a integrating with respect to y. That's what it corresponds to. Now, what's this actual area? Well, the area here would be, if I then flip it around, the area would correspond to the area under the curve for this fixed y value. So it would be being an area under a curve, would be another single integral of the value of the function at x, y, where what we're doing here is these are different x values. So the y here is fixed. Let's put a little star here to say that we're fixing the y value temporarily. And therefore, what we're doing is we're summing over small different bits of x. So what we're really doing is, one way of trying to decompose a problem is first working at the area of these side faces first, which really just corresponds to integrating with respect to x first. That's what it really corresponds to. And then once you integrate with respect to x, then you integrate the final answer with respect to y after that. So that leads, that sort of observation about how to decompose a volume into different segments then leads to the basic formula for how to approach this problem in general. And that is, you can do it for a rectangle two different ways. So that you can, like I just said up here, the way to do a double integral really is to integrate the x's first. So just integrate the inside function first with respect to x using a partial integral. And when you've got limits, plug the limits in just like you do normally. So really just subbing in normally, very much as you'd expect. You get an answer, and then once you've done that, that will give you the cross-sectional area, and then we're integrating that cross-sectional area over the whole y values this time. And that will give you the total volume. And that's trying to match up process to how you work at volumes visually. So you can do that. You can do the other way. So you don't have to integrate x first, you can integrate y first if you wanted to. And so for the moment, it's just a matter of swapping the order of integration quite easily. I'll talk more about that in a second. But you could integrate the y first and its limits, and then do the limits for x after that. So let's sort of see how that works in practice. So this sort of approach is called an iterative integral. And rectangles, you have complete choice. You can go one way or the other, no worries. For more complicated regions, which value you pick first, whether integrating with respect to x or y first, really is determined by the region you've got rather than by what you feel like. And so we'll talk more about that next week, or you might read about it. And so for rectangles, you've got more choice. But this whole process, though, of doing a double integral, or any other one for that matter, is going the inside first, getting an answer, and then keep working out. So it's working inside out. It's called the iterative method, effectively. And so what should happen here is that the limits, the inside limits, should correspond to the inside variable, and the outside limit should correspond to the outside variable. So in this case, as I've written it, C and D correspond to X, A and B correspond to Y. That's what that one says at the top. And that sort of carries through the rest of it. I don't know why I flipped it around. So let's just do a different sort of problem where we can't do it just visually. So let's find the volume under this particular surface. Now this surface here is a elliptic paraboloid going upside down, so it's a hill here. And I want to integrate it over a rectangular region, not square this time. So that's my picture. So I'm trying to work out the volume under this sort of shape here. And so you can imagine you've got some sort of tent. People tend not to make shapes like this. So I was trying to look at images of what they really look like for roofs. People do use curved roofs, but not in two different directions. I presume that's an engineering nightmare. But you can imagine a tent. What's the volume of a tent with this sort of shaped roof, for example? So how do you do that? So first of all, the general practice, I think, is to draw a picture of the region of integration, what you're trying to integrate over. So we want x and y, and so x is everything from -2, so from -2 to +2 even, and y from -1 to 1. And so it's going to be this rectangle here that we're integrating over. So that's going to be our region of integration. So we want to see what the volume of the surface above this particular region is. And by seeing the region, you can see what type of region is and how you decompose it. Rectangle is the easiest option, so we're not thinking too much about it just yet, but it's a good practice for later on. So our volume then would be summing in two different directions, so that's the double integral of our function, 8 minus x squared minus 4y squared, and we want to integrate with respect to both x and y. Now you can take a pick, it doesn't really matter. I'm going to pick integrating with respect to x first, and then y next. It makes very little difference in this situation, and therefore when I put the limits down, the limits for x have to be on the inside one here. So x goes between -2 to 2, and the y's are from -1 to 1. And then, as I said, the way to do this in practice really is to do the inside bit first. So just do inside out. It's pretty much the main advice. Just round brackets. So I'm leaving all the framework or the outside just there, just going to stick around for the moment. So I'm going to integrate the inside. So I'm integrating the inside with respect to x. So integral of 8 is 8x, integral of minus x squared minus x cubed on 3, integral of -4y squared is -4y squared x. And indeed, that was the partial integral we did a little while ago. Now that I've integrated, just like normal, I now set sub my limits in. So I'm writing it as -2 to 2. It's good to realise that what this means in practice that it's x equals 2 and x equals -2. And to begin with, since there's lots of variables floating around, it's easy to forget sometimes. So it's no problem typing it in. So the outside framework is the same. Then I'll plug in x equals 2. So that'd be 16 minus 8 on 3 minus 8y squared. And then minus the same thing by subbing the -2's in. So minus 16 positive 8 on 3 and positive 8y squared. Just is everyone okay with what I've done there? And if you add them all up, I realised that the whole thing's even in terms of x, so I could have saved my bit of effort by realising it's an even function, but I will. So collecting all the like terms together, you get 3 16s, which is 30, 48 minus 8, so you get something like 80 on 3 minus 16y squared, I think, by putting all the terms together. Notice that this second term is the same as the first one except for the minus sign, so it ends up being double the first term. So bearing any mistakes I've made, quite possible, that's what we've got so far. And so what we've done is we've just done the inside integral. So you can see all x's have disappeared. And so once you get rid of the x's, they should not come back in again. And so if they ever come back in again, you know you've made a mistake. And normally that happens next week when you got different, when the limits change a bit. So now we got to this stage. This is just now a normal integral we can do directly. So integrating with respect to y gives you 80 on 3 y minus 16y cubed on 3. And we can sub the limits in. We might notice this is even in respect to y, and so do the usual trick of doubling it and integrating from just 0 to 1 instead, because it's an even function. You don't have to notice that, but you can do those things as per normal. So subbing in 1, you get 80 on 3 minus 16 on 3. Subbing 0, you get nothing. And so if you do that difference, you get something or other. So 64, so 128 on 3, I think, is the final answer. So just recapping, how to do any double integral, I really recommend drawing the region of integration. From that will help you work out what appropriate limits are, and it, in the grand scheme of things, helps you work out which you should integrate first, x or y, too, for that matter. This case doesn't matter. Either choice is fine. Then once you've written your integral in term with the limits on it, just do the inside first, integrate, sub in, get an answer, then repeat. Do the next integral, integrate, sub in, and eventually get the answer. That's the way of doing it. So, just a little tip about stuff is that for rectangles, you can choose to integrate x first or y first. You can go either way, it doesn't really matter. And you can do it with very little modification to how you do stuff. For when you swap order integration for other regions, it's a bit more complicated, which we'll have to come back to later. But certainly for rectangles, it's a good trick and sometimes really important to do. So let's just have a really quick go at this one. This is the region, and looking at it now, it looks different to what it before. So this is the surface y sine xy. So you can see it actually follows the axis. It's actually on the axis 2 points and then rises up really highly as you're getting away. Copy the wrong one. Okay. So if we look at this integral as written, so it's integral from 0 to 5, 0 to pi. So it's basically integrating over a rectangle. And as I said, I still like the idea of just drawing the integration. So y is the inside is between 0 and pi. And the x, which is the outside, is between 0 and a half. So we're integrating over this rectangle here. So I've just translated the limits into a picture, essentially. If you imagine doing the inside bit first, if I'm integrating respect to y first, I integrate y times by sine xy. That's a product of two different things, and so I'm going to have to try to use integration by parts to try to get that done. And I'm going, oh, it doesn't sound very nice. Maybe I'll just try the opposite way, maybe the integral's easier. This common happens, that sometimes this inner one as written is difficult, swapping the order of integration can make it easier. And that's always a good thing to have in your mind. If the inside go, well, that's pretty beastly, maybe that's a trick to swap the order of integration. And you might find that in assignment too. And so that's what I'm going to do. And to swap the order of integration requires two things. One, the easy bit is just to swap the dx and y in opposite order. Then you also need to change the limits. For rectangles, that simply means just swapping the numbers around. Just put in and change the order. For more complicated regions, you need to do a little bit more effort than that. We'll go back to that later. So now I've swapped the limits for rectangle and straightforward. Again, let's just integrate the inside one. So we got an integral with respect to x. The y here is just a constant now. So it's really just integrating sine of xy. The sine xy here is linear in terms of x, so I can use like reverse chain rule, for example. So doing reverse chain rule, integral of sine would be minus cos xy. Let's put the minus on there. The y is still floating around. It's constant respect to x, so just staying there. And then because it's reverse chain rule, then I have to divide through by the derivative of the inside function. So I have to do the partial derivative of x, y respect to x, which gives me y, and they cancel each other out, which is nice. And then once I've integrated, I've got to sub in x equals 0 up to x equals a half. So stop me if you need to. So it's reverse chain rule. If you don't like reverse chain rule, you could do substitution. You could have let u equals xy, and then worked out what du is y dx, and go from that way. You can do substitution as well if you needed to. But anyway, back to as it's written. So you're going to get from 0 to pi. Sub in a half gives you minus cos y on 2. And subbing in 0, cos of 0 is 1. So it's minus 1 gives you 1 minus cos y on 2. You run that respect to y, and then just integrate as written. Integral of 1 is y. Integral of minus cos y on 2 requires reverse chain rule again. Integral of minus cos is minus sine y on 2. And then we have to divide, because it's a reverse chain rule, by the derivative of the inside function, which means dividing by half or multiplying by 2, same thing. And then we're chucking in 0 and pi. Subbing in pi, getting pi minus 2 sine pi and 2. Sub in 0, you get nothing in this case. Sine pi and 2 is 1. So the final answer is pi minus 2 in this instance. If I haven't made a mistake, that is. So reverse chain rule was useful in my mind because it meant I didn't have to write all the other substitution bits on the side. But if you need to do that, you can. If you're going to do that, you're going to have to go, I'm just going to focus just on the inner one for the moment. So inner integral equals blah. Oh yeah. No, yeah. So because it's subbing in 0, the 0 clobbers the y in this instance. So I do make mistakes though. So thank you for keeping your eye out on me. That's good. So just showing you that's like swapping order integration is a really useful problem-solving technique. And so when you do these style integrals, don't always just do the inner one directly as stated. You go, wow, that's hard. Swapping might have helped. Like you could have done it directly using integration by parts, probably. So if you differentiate that one, you have to integrate that one. So it'll get messy, integration by parts, but you could persevere and get through it that way. But often swap integration, much easier. So just recapping, we did a bit of revision on assignment 1, so hopefully that last minute helped, and then focused on just introducing double integrals, which is just volume under a surface, above rectangular regions. Looked at the main way you're going to approach it is using the iterative method, so inside out, and then looked at one trick, I guess, so one more advanced method, and that's swapping auto integration. And that's a good way of solving harder problems. So what we'll do next week is looking at integrating over more generic regions, which require a few more things. But it's good to practice this first, just so you've got the basic ideas of what's required here first. So that's what I encourage you to do. Just before we say goodbye for today, though, do you guys have any questions about what we've done today, or you have got a moment? Actually, I've got one more question about the assignment. If not, that's okay. I thought I'd ask. All right, well, thanks very much for coming, and make sure you put the assignment in on time, so which is tomorrow evening, as it stands. And otherwise, I'll see you guys next week. So catch you later. Thanks very much.